Problems are going to be a little bit more complicated in the first video on the gas laws. Looking at this particular problem, it's actually a number of problems all put together here. The first one says that nitrogen gas can be collected by water displacement. So here we have nitrogen gas being produced by some kind of a chemical reaction. It's going to flow through this tube. It's going to bubble up into this space here. And the space here is going to contain both nitrogen gas and water vapor. And we're told that the total pressure of the mixture of gases is 788.8 millimeters of mercury, and water at that particular temperature exerts this kind of a pressure, and we want to figure out the pressure of the nitrogen. We can apply Dalton's law of partial pressures to this, where the total pressure is the sum of the pressure of the nitrogen and the water, in this case, the sum of all the partial pressures. So pretty simple problem, substituting in. We have the total pressure equaling the pressure of the nitrogen plus the pressure of the water. Subtracting, we can get a pressure of the nitrogen to be 760.6 millimeters of mercury. Second part of the problem, we're told if the total volume of the gases collected in the above problem is 14 milliliters, and a certain temperature, what is the volume of the nitrogen gas? Here we need to think about the relationship between pressure and volume, and the partial pressure of the nitrogen is to the total pressure as the volume of the nitrogen is to the total volume. In other words, those two are directly proportional to each other. And so we can just substitute in from the previous part of the problem. This is the pressure of the nitrogen to the total pressure, and that equals the volume of the nitrogen to the total volume. Cross multiplying and dividing will give us a nitrogen volume of 13.5 milliliters. Then we're asked to use the ideal gas law to calculate the mass of the nitrogen gas collected in the above problem. To get the mass of the nitrogen gas, we first have to get the number of moles. And so we are given the pressure in millimeters of mercury. We'll have to convert that to atmospheres. We're given the volume as 13.5 milliliters, the temperature as 22 degrees Celsius, and so we can convert to the appropriate units for the ideal gas law. We take the pressure of the nitrogen, divide by 760 to convert to atmospheres. We convert the volume into liters, we convert the temperature into Kelvin, and we can solve for the number of moles as 5.58 times 10 to the fourth moles. This is of the nitrogen gas, diatomic. To get the mass, we just have to take the number of moles then, multiply by the molar mass, and that gives us the number of grams. So here we see Dalton's law being applied a few times. And other relationships as well. Take a look at another problem. Here we're asked to solve for the volume of hydrogen gas. So the last part, what is the volume of the hydrogen gas? But we're given information about a reaction of magnesium and hydrochloric acid, and it's collected over water at 24 degrees Celsius. We're given a total pressure of the hydrogen gas and water vapor and a partial pressure of water vapor. So to solve for volume, we need to know the number of moles. We need to know the temperature. That's pretty much given. We'll have to convert to Kelvin. And we need to know the pressure. We can solve for the number of moles by writing a balanced chemical reaction for this reaction. So we have 4 grams of magnesium, and we want to find out moles of hydrogen gas. So we have to go grams to moles, and that'll give us the moles of the hydrogen gas. So that calculation is going to look like this. We have 4 grams of magnesium. We divide by the molar mass to calculate the moles of magnesium, and it's a 1-to-1 mole ratio from the balanced equation, and that'll give us 0.165 moles of hydrogen gas. And to solve for pressure, here we need to apply Dalton's law of partial pressure. Pressure of hydrogen is going to be the total pressure minus the pressure of the water in that mixture of gases. And then to convert to atmospheres, we're going to divide by 760. So the total pressure equals the sum of the pressure of the water plus the pressure of the hydrogen. Subtracting the pressure of the water will give us the pressure of the hydrogen. We can then plug all those numbers into the ideal gas law. Here is our number of moles. Here is R. Here's the Kelvin temperature. Here's the pressure in atmospheres, all in the appropriate units, so that we'll end up with 4.12 liters as the final answer. In this problem, we're told that an empty syringe has a certain mass. When you fill it with to a certain volume with a certain gas, you get a mass of 45.85 grams at a certain pressure and a temperature of 20.5 degrees Celsius. What is the molar mass of the gas? The units for molar mass are grams per mole. So to solve this, we need to know the mass of the gas and the number of moles of the gas. To get the grams of the gas, we are given the mass of the empty syringe and the mass of the syringe with the gas. So the gas by itself can be determined by simple subtraction. The syringe with the gas minus the empty syringe gives you the mass of the gas by itself. To calculate moles, we just have to use the ideal gas law. We'll have to convert our pressure into atmospheres. We'll have to convert our volume into liters. We'll have to convert our temperature into Kelvin. And that will give us this setup. And so here is the pressure converted to atmospheres by dividing by 760, the volume in liters, temperature in Kelvin, and that gives us a certain number of moles. So now we have our grams and our moles. And to get the molar mass, we divide the number of grams by the number of moles. So this gas turns out to be 75 grams per mole. Next problem is going to be very similar to it, only in this particular problem, we are never given the mass of the empty syringe to figure out the grams of the unknown gas. So in this problem, we're going to have to calculate the mass of the empty syringe. To do that, we'll need moles first. And so let's start with the calculation of moles. Again, rearranging the ideal gas law, number of moles is going to equal PV over RT. Converting into all the appropriate units will give us a number of moles of 5.372 times 10 to the minus third moles. Now, to get the mass, we need to know the mass of the unknown gas. We know that the unknown gas has a mass of 76.477 grams in the syringe, but we don't know the mass of the empty syringe. However, we know that the original syringe had argon gas, and now we know the number of moles of argon gas, which means we can calculate the grams of argon in the syringe, and by subtraction we can then get the mass of the empty syringe, which then will allow us to calculate the grams of the unknown gas. So first thing we need to do is to take that number of moles in the syringe. And by the way, according to Avogadro's hypothesis, any gas with the same pressure, same volume, same temperature will have that number of moles. So this is not only the moles of the argon gas, but also the number of moles of our unknown gas. But by multiplying by the molar mass of argon, we can get the number of grams of argon. Then to calculate the mass of the empty syringe, we can take the mass of the syringe with the argon gas, subtract the empty syringe, and now we know our mass of the syringe with the argon minus the grams of argon gives us the mass of the empty syringe. That then allows us to calculate from this number the grams of the unknown gas. So the first number here is the syringe with the gas. We subtract the empty syringe, and now we know the number of grams of the gas. At that point, we have the grams of the unknown gas and the grams of the argon, again, which is equivalent to the unknown gas because of Avogadro's hypothesis. So to get the molar mass, we divide the grams of the gas by the number of moles of the gas to get the molar mass, and we're asked to identify what common gas this could be. 32 grams per mole matches the molar mass of oxygen, giving us the possibility that that is oxygen gas.